Welcome to Power Corner. I'm your host, Alia Shokat, editor-in-chief of Power Electronics News. We're here speaking with Chris Butler, president of Embedded and Critical Power at Flex. So, hey, Chris, how are you doing today?
Doing great, and thanks for having me.
Great to have you. Thank you. I appreciated the conversation we've had so far, and I was hoping we could talk about all of these things in a little bit more detail. And let's just start off with the challenge and shifting to the 800 volt DC data center architecture.
Yeah, so this has been a hot topic in the industry over the course of the last year. It's kind of funny because even a year ago, people were still talking about plus minus 400, and
Yeah.
bringing DC into the data center was a pretty transformational idea. Over the course of the last year, I think people have been getting more and more comfortable with the idea of 800 volt being the de facto standard in the data center. But I think the things that people are starting to realize is, we're talking about making a very dramatic change in an industry, at least on the power side of the industry, that doesn't change that often. I mean, this is a once in a generation, type change that we're seeing in the industry right now. And so there's a lot of things that need to happen in order for 800 volt to really take off. We are designing 800 volt DC systems. So I think it's a foregone conclusion that 800 volt DC is going to be used. And there are some clear advantages. Obviously, you push the voltage up, current goes down. That allows you to reduce the size of the conductors. It also has some benefits on efficiency. When we start talking about things like rack density, you just can't achieve the rack densities that we're talking about in some of these newer chip designs without increasing the voltage. But it's kind of interesting, the chips still operate at, just under 1 volt DC. So there's a very, significant effort in trying to figure out how to get that 800 volt down to 1 volt DC in a very efficient way. So I can talk a little bit about what we're doing there on that side of the equation. But then you also have to figure out how you're going to get that 800 volt distributed through a facility in a safe manner. Today safety standards are still evolving, and so there's a lot of discussion about how an 800 volt DC system will behave. Protective devices that are in the systems today may or may not operate the way that they would under an AC load. Spent a lot of time in the breaker industry through my career, so we've been looking at this and very careful about how we deploy protection strategies within the data center architectures as well, because that's a huge driver of being able to operate these systems safely.
Safety at 48 volts is very different than safety at 800 volts.
Yeah. And I think, just to carry that point a little bit further, the safety standards that are in place today, and the latest generation of these were really developed in 1995, NFPA 70E. That was when the first, draft of the standard was written. It took 20 years before they were put into practice. They really weren't widely recognized, and people weren't taking them seriously and implementing PPE until 2015. And so if you think about that long of a change, right, this is the thing that I try and get across to everyone. We're in an industry that takes 20 years to change, and we're asking it to change over a 12 to 18 month period. It's something that I've never seen before in my 30 years in the power industry. And it's exciting, but at the same time, I think people have to realize that there's going to be an ecosystem that needs to be built up. There needs to be standards built. There's a tremendous amount of work that's being done to make 800 volt a reality. And that's really where I think, our organization is doing a tremendous amount of work, trying to make that all happen. And it's more than just developing a product and going and issuing it to a customer. There's a tremendous amount of work going on at an industry level. to
Yeah.
make 800-volt a reality and safe.
Could
So.
you talk about that a little bit more, those challenges, particularly in safety? I know that, solids, that you have technologies, obviously mechanical circuit breakers of the past, but you have, the potential for solid state circuit breakers today and other DC protection devices. Now there's e-fuses, et cetera. But could you talk about some of the challenges in reaching 800 volts and maybe in context of safety?
Well, let's first talk about where 800-volt is going to be deployed in the very near future,
Yeah,
right?
yeah,
So what's happening right now is people are developing something called a sidecar. This sidecar and Flex has a sidecar as well, and we're
yeah,
developing and deploying this product. We're ramping production as we speak, so it's a reality, and it's going to be deployed in data centers soon. When you start looking at that sidecar technology, basically what that is that's a power rack at the end of the IT rack.
mhm,
So up until that point, everything's still AC. It's the old way.
yeah,
Okay. And the reason why, these standards were developed is, we want to make sure that the server racks are prepared for 800-volt DC, but then we also realize that the infrastructure that's being deployed isn't going to change very quickly, right? So 2 years ago, right, people were, making decisions to invest in data center construction and getting through, codes and standards and getting building permits and all of that. You're not going to change that now. Those buildings are going to be built with the power systems that were intended for those buildings and approved. And
yeah,
so what'll happen is people take that 400-volt AC power, drop it into this sidecar, and then they can start deploying 800-volt DC racks
mm,
without having to reinvent the data center. Now,
yeah,
future data centers are going to be reinvented. We'll talk a little bit about that in the next step. But
yeah,
for right now, that sidecar is where the 800-volt enters the data center.
mhm,
So we're really only talking about this safety challenge in the IT rack itself and this sidecar that's feeding that IT rack.
mhm,
So it's kind of enclosed, right? It's
yeah,
it's not a problem that is pervasive throughout the entire data center yet. And so if you look at the concern that we have within those racks, right? Common operations that you have today where someone is just racking out a server and putting a new server in. When you're dealing with a 50-volt server, that's not a big deal. That's considered relatively safe. In fact, it's recognized by OSHA as safe, where you don't even need any personal protective equipment to rack in or pull out that server.
right. And you got
Well,
the blind mate connectors and
exactly.
yeah,
Yeah, exactly. Now you go to 800-volt DC, even with a blind mate connector,
yeah,
if something goes wrong, you could see an arc flash
yeah,
in that rack. So, these are the types of things that we're working on with customers to ensure that, number one, they can do these types of operations safely, or we change the way that they operate, right?
mm,
And so these are some of the things that are being discussed. You can do things like power capping through solid state circuit breakers, but to be honest, there aren't really a lot of solid state circuit breakers on the market today that can achieve this.
yeah,
Um, you also have a challenge with an 800-volt DC server being plugged into a hot bus. You need to pre-charge those
mm,
systems. When you plug a high-powered electronic like that onto a bus, you're going to
mm,
see an effective short circuit until the capacitors are energized. And so
mm,
you need to have some circuitry built into that server to prevent that short circuit condition from taking down
yeah,
the rest of the servers in that rack. So
mm,
these are the types of things that are being worked on. The reality is the servers today, even though they're using these more high-powered chips, are still working with a 48 to 50-volt input voltage.
yeah,
So even though you have an 800-volt DC rack, people are using a power supply unit within that rack, converting that 800-volt down to 50 volts. And then
yeah,
they have a separate 50-volt bus within the rack. So we're in a very transitional stage right now in the world of 800-volt DC. The server hasn't evolved to be a native 800-volt DC server.
yeah,
That's still probably 18 months off into the future.
mm,
So you're still talking 50-volt servers that are being plugged onto the
mm,
bus.
mhm,
The 800-volt story within the power distribution of the data center is really only limited at the rack level today.
mhm,
So these are the things, everybody's just kind of dipping their toe into the water of 800 volt right now. And like we see this all changing very, very soon and very dramatically, but
Yeah.
it's still probably somewhere in the world of 18 to 24 months before we see native 800 volt DC systems really being deployed.
And when you talk about moving from the sort of 50 volts servers to the 800 volt, what do you see required to make that transition? Yeah.
So there's a couple of things. I mean,
Yeah.
number one, in order to plug onto that 800 volt DC bus, we're going to have to figure out how to do that safely. So that's number one.
Yeah.
Number two, it takes a lot of power electronics to take 800 volt down to, the workable voltage of some of these chips is like 0.6 volts.
Yeah.
Right.
Yeah.
So if you think about how that works today, today we take 480 volt AC, we take that to 50 volt DC. That 50 volts is then transformed to 12 volts. That 12 volts is then transformed to like 0.6 volts. So you have all of these transitions that happen. In an 800 volt DC scenario, you still have to do these multiple steps. So you may go 800 volt to 50 volt, 50 volt to 12 volt, 12 volt to 1 volt. I mean, you're talking about a number of transitions, and that all would have to happen on the server board itself.
Yeah.
So today, those power transitions are happening in big PSUs that are installed somewhere other than the server. In an 800 volt native server, you're going to have to put all those power electronics in the server board itself. So the industry is calling that the PDB, a power distribution board that'll sit inside the server. But remember, that's not only going to be limited to power conversion. We're also going to have to put some safety mechanisms in these circuits as well. Mm-hmm. So this is something that, today everybody is actively developing so that, you can get to the point of an 800 volt native server. Today, everybody's still deploying, the traditional 50 volts. And so, the question is when do the physics require us to be native 800 volt in that server to achieve the rack densities that we want to have? Because to me, the thing that's going to drive this industry, the thing that is driving this industry to 800 volt are the physics of what we're trying to accomplish here. Mm-hmm. You physically can't fit enough bus in the rack to deploy, a 1 megawatt rack, which is our 600 kilowatt rack that people are envisioning with 50 volt DC. You just can't do it, right? So mm-hmm. in order to get to those types of rack densities, you're going to have a native 800 volt DC server.
Yeah.
People aren't deploying at those rack densities yet. And that's giving them some flexibility. In fact, if you look at NVIDIA's DSX designs, they're all in this hybrid mode still. And I think they will be in this hybrid mode still until the next chip generations. It may be Feynman before we get to a point where...
So when you say hybrid, do you mean like 50 volt to... Okay, gotcha.
You'll see at the top of the rack, it's 800 volt coming in. It's 50 volt going to the server. So you'll see two bus systems in the rack itself. And so this hybrid, situation is going to be around at least for the future. That actually is somewhat of a good transition for the industry as well, because you still have things like, networking hardware and things like that are still operating at the lower voltages that are also going to have to change, whether it's AC feeds that they have today that are going to go to DC, or they're using 48 or 50 volt DC as well in the network switching and those types of topologies. So there's a lot, it's not just the server. It's all the other stuff that goes around the server as well. I mean, we're even looking at 800 volt DC CDUs.
Okay.
Right? Because the cooling, if you're going to have an 800 volt DC data center, everything in the data center, you're going to want to have work on 800 volt DC. Mm-hmm. So people are all shifting their way of thinking of, okay, is there a benefit for being on 800 volt DC? How do I go to an 800 volt native DC data center so I don't have to have a combination of AC and DC? I think it's interesting to see even NVIDIA's latest white paper that came out last week. They're introducing a hybrid AC DC model now too, because they're realizing that the industry is not ready for a full 800 volt native, 800 volt DC native data center yet. It's close. And we're making a lot of strides to get there, but there's still a lot of work to be done in the ecosystem before we're ready to really scale the industry at 800 volt.
Yeah, yeah. Um, well, I mean, shifting to that 800 volt native architecture, what are some of those systems that really need a shift? You mentioned the 800 volt CDUs. I understand that, solid state transformer technology is involved in stepping down that grid voltage to 800 volts and the distribution there. But could you talk about that a little bit more in your
Yeah.
understanding of how to move there?
So let's talk a little bit about how that 800 volt is generated today.
Yeah,
So today in the sidecar setup, right, you're dealing with a system that is roughly 97.5% efficient. Okay, so you're already at a high level of efficiency, right, in that 800 volt DC conversion from AC to DC. But people are looking at solid state transformers of getting us into the realm of 99+% efficiency, and that's just that one conversion step. If we can also get additional conversion steps out of the equation through the use of a
yeah,
solid state transformer, you can actually probably get somewhere in the neighborhood of a 5-point efficiency gain. Now, some of my competitors are out there talking about a 3-point conversion, 3-point improvement in
yeah.
efficiency. I think it's going to be a little bit closer to 5, and that's only the
Mm,
power efficiency conversation.
yeah,
There's also, in addition to that, a whole conversation we could have about cooling. But
yeah,
I think the reason why people are saying it's a lower efficiency gain is they're not thinking about the entire system.
mm,
So when I look at the current systems that you have today, right, you've got a medium voltage transformer up at the utility entrance of the building. Then you're going to low voltage. You have PDUs in there that also have some losses, because there's transformers in power distribution units that sit on the data center floor. A lot of times you'll have a UPS in the circuit as well. And UPSs in an online configuration are generally about 96% efficient.
yeah,
Maybe in some of the power saving modes and some of the new SiC based models, you can get into the 98s, but generally you're talking 96 to 98% efficient. Every time you put another inefficient, puzzle piece in the single line diagram, you're degrading the overall system efficiency.
mm,
So the way I view this is, I think we're going to have to simplify the way power is distributed in a data center. I presented at OCP last year a vision of 34.5 landing somewhere either on the data hall floor or near the data hall floor. I think people aren't comfortable with 34.5 sitting in the data hall yet, but we could put a brick wall in between and be very close. You could have 34.5 kV coming into a solid state transformer,
mm,
that solid state transformer feeding 800 volt DC out, all the other ancillary systems, including the IT load being on 800 volt
mm,
DC. And now you've taken a power system that used to operate in the range of 89 to 90% efficient,
yeah,
probably closer to 95%, because you're eliminating that old transformer technology, you're eliminating the UPS, that solid state transformer, if we think about it the right way, can provide backup, right? It can
yeah,
provide, the attenuation that we need to run AI loads. So that load variation that we were talking about earlier,
yeah,
it can provide that level of attenuation up at
yeah,
that medium voltage level. It can also provide some form of resiliency to the system, right? So
yeah,
if the grid sees some challenge, it can inject power where it needs to keep the IT load stable and vice versa.
mm,
So you end up with a one system approach to delivering that 800 volt DC power to the server, and it's all really at that entry point of the SST. And if we can do that all in that envelope, you end up with efficiencies, at least at that level, right, in the 98 to 99% range. And then the only other area that we haven't solved yet is how do you get that 800 volt to 0.6 volts in the most efficient way possible.
yes,
That
yes.
the industry
How?
hasn't solved that yet, because
Okay.
honestly, that's where a lot of the power is lost, is in all
Yeah.
those conversion steps that we have. And The holy grail would be to say, hey, we have this great power module that goes 800 volts to
Straight
zero point
to
0.6 volts.
point 0.6.
We have a lot of smart people that have been at this for many, many years. We're not there yet
Well,
as
those
an
800
industry.
volt to 6 volt PDBs are still, pretty cutting edge now. And from what I understand, I mean, you've got, thousands of amps running through them. They're double side cooled, and a lot of them are using GaN. But I would say that's quite a shift, is it not?
It is, and we're at the forefront of that with vertical power delivery,
Oh,
and
right. Yes.
as
Yeah.
you said, with sandwiching this between cold plates and things like that to make it as efficient as possible. You're still in this 95-ish range of efficiency when you look at all those conversion steps. So
Yeah.
if you take that and apply that with like a 99% SST, you're in that range of 94, 95%, which is still a big step up from where we were. And, I think for a long time, we've always looked at efficiency as saving power.
Yeah.
I mean, that's always been our mindset. Today, this is more about squeezing out more tokens. This
Yeah.
is less about, this is really less about, hey, I want to save, a couple of, I
More
want to save
tokens
some
per
money on
watt.
my electric bill.
Yeah.
It's about the token per watt story. And, a lot of people, they don't know if that's the most efficient way to measure efficiency, right, in a data center. And they're probably right that that's probably not the right way to look at it. But really, at the end of the day, if you look at the opportunity cost of presenting one more token, that's a lot more valuable than saving a kilowatt, right, on energy. So that's the way people are looking at it today. It's going to make the investment case for these data centers better. And on top of that, right, we obviously have a very close look at the efficiency of these data centers because of the environmental impact that they're bringing, right? I mean, data centers are going to be built. I don't think we can refute that statement, right? People have an insatiable demand for some of the capabilities of AI and what it, the value that it brings to, the society. So we're going to have to figure out how to do this in the most efficient and environmentally responsible way possible. And so that's also why we're investing in looking at the entire system, not only from a power efficiency standpoint, but also a cooling efficiency standpoint.
Yeah. Can we talk
Because
about
look,
that a little bit more? Yeah. Yeah.
I mean, look, a couple of years ago, 50% of the power going in the data center was all going into cooling.
Yeah.
That's come down a little bit. I mean, it depends on what study you look at. Maybe it's 30 to 40% now, but it's still a major consumer of power in the data center. So, I think, one of the things we're starting to see customers look at is, hey, reducing the amount of fans improves power efficiency. You go to liquid cooling, you're eliminating some of that as well. So there's some, depending on the cooling media that's used, you can actually have some improvement, right, in energy consumption and cooling, the thermal transfer, right, of heat. You're also looking at now other chiller technologies that are more efficient than they were in the past. Closed loop systems, dry chillers are starting to be looked at as another way of running the data center at a higher temperature. You'll start seeing NVIDIA talking about higher coolant inlet temperatures. I mean, I don't think people are very comfortable going much above 40 to 45 degrees C, but we are hearing talks in the industry about even pushing that further. And maybe pushing that further maybe drives people towards more of a two-phase cooling solution, which I don't think is, the industry is sold on that being the answer today because of the complexity associated with it. But look, there's going to be some tipping points in the cooling equation as well here. Right now, you got a lot of people focused on 800 volts and building the ecosystem around that. Cooling, you can see a lot of the investments that people in the industry are making in cooling because that's as important as the power consumption side, if not more important in the future. So, I think that cooling technology, these are all going to come together, right, into a new architecture design. And that's one of the things we're excited about because we're building we're building these systems end to end to experiment with some of these technologies to see what the best outcome can be.
Yeah.
And so that's what I'm super excited about. Like we're getting to experiment now, and we're seeing really meaningful changes, right, in the efficiency of these data centers moving forward. So
Very exciting stuff. Well, Chris, maybe we could talk about the grid aspect of the data center. Just on the we talked about the efficiency. Can we talk about Flex and its work with utilities a little bit more
yeah,
and how that
so
relates?
yeah, we've been investing a lot in the utility space. I mean, our first acquisition in the utility world was Crown Technologies back in late 2024, and we made that acquisition primarily because of the fact that, we were building more modular systems and Crown was building modular systems for the utility business. And a light bulb went off in our head that it seemed like every opportunity that Crown had was related to a data center or a data center that was going to be in construction. Mm-hmm. And the systems that Crown provides are systems that sit at the substation level within the utility. And so it's like kind of that last mile connection point, that interconnect between, the data center and the utility. And so they were providing medium voltage systems and intelligent relay systems for the substation controls. And, that's when the light bulb went off. And we actually acquired another business earlier this year, EP Squared, out of Des Moines, Iowa, which does a very similar type of, in a very similar capacity, relay panels and substation controls. And so now we cover the entire US with this capability. And as we start talking to utilities, we're starting to realize that, the two worlds haven't met yet, right? The utilities are still, trying to improve their infrastructure. There's a lot of challenges that they face because it's a regulated industry. And, tremendous amount of work is being done for them to get the capital needed, to be able to deploy, larger substations, more generation capacity. In some cases you have generation capacity, but that generation isn't connected to where the data center is. So again, and that's where you're seeing these interconnect delays, because they have to have not only the generation capacity, they have to have the transmission and distribution right where the point of load is going to be. So we've been getting involved more and more in helping our utility customers marry the data center needs that are out there in the future with some of our capabilities, so to help improve that interconnect. But now we're starting to see a whole new dynamic happening where you've got all of these data centers which are becoming a bigger consumer of power on the grid. A year or so ago, I think the numbers were somewhere in the neighborhood. It's about 10% of the overall utility demand in the US. And, we're expecting that to double over the next couple of years. But a data center load is very different than a traditional load that you have on the grid. So, traditional loads are very dynamic. You come home from work at night, you turn the lights on, you turn the lights off when you go to bed in the morning. It's a very dynamic type of load, right? That changes throughout the day. Industry comes online, right, during the day. Then you have things like, higher temperatures in the afternoon, so more air conditioning load on the grid. So all these things are very dynamic. A data center is a big static load, right? It doesn't change very, very typically. And, with AI, while you have this dynamic condition with these, spikes and peaks and valleys,
the load profile is still predictable.
The load profile is very, very dynamic. Really at the end of the day, it's a static load on the grid. So there's a couple of challenges that's presenting. Obviously, you have all the noise, right, that's created by that and the impact that has on the neighbors of the data center. So these spikes and power abnormalities have a big impact on not only the efficiency of the grid, but how the grid behaves, right? When you have a lot of this new nonlinear load coming onto the grid. So that's the first problem. And so people are working, we have a product called a capacitor energy storage system that is, sits near the server and helps attenuate some of those load abnormalities. You see customers using things like battery energy storage systems up near the point of common coupling, which also have an impact on that. But that's only addressing the power quality problem. There's another big issue, and it really came to light the end of July in Northern Virginia, where there was a significant amount of IT load that was dropped all at once. And so, you would think that a grid operator would be excited when, the load profile goes down and they have more generation capacity, but that's not really the case. When a load drops on a grid, it can actually damage generator shafts and things like that. It can have a tremendous impact on the grid itself. And so in this particular case, what happened was there was a little disturbance in the utility voltage, and all the UPSs in the data centers in Northern Virginia said, oops, we have a problem, dropped the load, and everything went to UPS. And so it was a problem that persisted on the grid for over 10 minutes because they weren't prepared for this significant drop in load instantaneously. And that's driving the utilities now to get together. This is already a thing down in the ERCOT utilities down in Texas, where battery energy storage was a requirement. Now the broader utilities in the US are looking at, PJM is looking at implementing a grid code that will require energy storage on any load greater than 75 megawatts. So the utilities right now are trying to figure out how to deal with these demands. And then you have, they've changed a lot. I was on a panel earlier this year with, the head service planner for Dominion Energy, and they've changed the way that they've structured contracts and things like that so that, data centers are not really a burden on the utility from an economic perspective, which that wasn't always the case. It could be a data center came and said, hey, we're going to use 100 megawatts of load. And then that 100 megawatts of load was installed and they never actually used it all. Maybe they used 80. And that created an inefficiency for the grid operator. Now they've changed the contracts. And by the way, that also created an impact for the other people that are customers of that utility. I think that's why in the general public, you're seeing this sentiment that data centers are bad on the utility. Well, the economics of all of that have been fixed, right? It's really now, how do we deal with this, significant increase in load and a different nature of load than what the utilities have traditionally dealt with. And, I think there's been some great advancements in, some of the power conversion technologies. They're a lot more reliable. They're a lot more efficient. You couple that need with the need for inverters. Well, grid forming inverters, yes. So you've got the grid forming inverters. You couple that with the need for a clean 800 volt DC source that's needed. You bundle that all together, and you have a much more simplified power delivery system within the data center itself. And I think you'll get to a much more efficient system as well, because you'll eliminate a lot of those conversion steps in the AC world. And then we need to go work on the DC world, as we were talking about earlier, within the rack, and trying to figure out how to get that to be a more efficient conversion down to the chip level. So.
Fascinating. Thank you. So I can keep asking you questions.
I did talking for a long time. Yeah.
I know. I did want to. Sorry about that. I did want to cover real quick. Could you talk about Flex? The spin out a little bit more, and what what's going to happen there, and then that's my last question. No more.
So I think maybe some of your listeners are aware. We announced back in May of this year the intention to spin out our data center utility business. Likely happen at the beginning of 2027. Basically, the intention behind that is really clear. Obviously, there's a tremendous amount of growth, right, in both the utility and the data center industries, and it's going to demand a lot of focus from our executive staff. And so we do think it's time. It's grown to be at the end of our last fiscal year was $6.5 billion. This year, we think it'll be over $10 billion. We're still on track to delivering that right now. And so we're super excited about the growth the growth trajectory of that business. And honestly, if you think about the rest of Flex, right, the contract manufacturing business within Flex, unfortunately, a lot of the dollars and the attention were going to the data center business. So, it's a great opportunity for the members of our Flex team to, have maybe, another chance to invest more in their businesses as well and drive growth. So, it's really the best of both worlds for both pieces of the company, right? Flex's heritage of being a very strong contract manufacturer needs investment as well. And unfortunately, the capital allocation was, skewed towards the data center side over the last couple of years. So we think it's a win-win, for both sides of the company. And it's going to give us a level of focus in the data center world, that allows us to approach an industry that really hasn't changed in 100 years in a very novel way. So that's what I'm super excited about.
Accelerated way too.
Exactly, right? We're taking 100 years of heritage and industry standards and trying to change them over the course of 12 to 24 months, which is an exciting challenge to take on.
For sure. Well, thank you so much for your time, Chris. I really appreciated it. I really appreciate the conversation. I learned a lot myself, so thank you.
Cool. Thank you. Appreciate the time.